Hello friends, today we are going to discuss amplitude modulation from the subject Foundations of Communication and Computer Network. In the last lecture we have seen first type of amplitude modulation, that is double sideband full carrier. In today's lecture we are going to discuss double sideband suppressed carrier, that is DSB SC. Actually, carrier does not contain any information. All information that we want to send is present in sidebands only, that is upper sideband and lower sideband. As carrier does not contain any information, why it is necessary to send? So, AM signal is derived in previous section. This was the equation we have already designed in last lecture. So AM signal has three components. First one, unmodulated carrier, LSB and USB. The message to be transmitted present only in LSB and USB. We consider power relation is given by amplitude modulation power, or P total is equal to PC into bracket 1 plus n square divided by 2. The power required for carrier component is given by PC is equal to P AM divided by 1 plus m square divided by 2. We can put modulation index as m is equal to 1 in the above equation. So the equation becomes PC is equal to 2 by 3 P of AM. So DSB SC method is inefficient and therefore wasteful method. 2/3 of the transmitted power appear in the carrier, which is not contain any information. That means carrier signal requires 2/3 of the total power. So the real information is present in sidebands only. So suppressing carrier is the method here we are going to implement. Is 2/3 of the power is saved due to this DSB SC method. Here, modulated signal of suppressed carrier can be given by the equation DSB SC is equal to E of AM minus PC. As we know, instantaneous value of carrier EC is EC sin omega t. Put this value in equation 1. So, the equation becomes E of DSB SC is equal to E of AM minus PC sin omega t. Substitute E of AM from equation 2. DSB SC gives EC sin omega t plus m into PC divided by 2 into cos of omega c minus omega mt minus n by 2 PC into cos of omega c plus omega mt minus PC of sin omega t. Negative positive terms gets cancelled with each other and then equation becomes E of DSB SC gives m into PC divided by 2 cos omega c minus omega mt minus n by 2 PC cos of omega c plus omega mt, that is only two terms with LSB and USB. DSB SC technique adds complexity at the receiving point to recover the message. When cost of receiver is low, then AM is preferred in equation A. When point-to-point service is there in application, then DSB SC is preferred. Next, frequency spectrum of DSB SC, which is shown in this frequency spectrum. Only LSB and USB spikes are shown by suppressing carrier frequency. USB represents FC plus FM frequency and LSB represents FC minus FM frequency. Bandwidth is required for DSB SC is twice the frequency of modulating signal. That is the difference between two frequencies, which is shown here f of USB minus of LSB which gives us bandwidth of DSB SC is equal to plus 2FM. Then next, amplitude of DSB SC. So according to the amplitude of DSB SC, the maximum amplitude of DSB SC modulated voltage varies according to the modulated voltage changes as shown in the wave diagram. When there is an modulation, instantaneous value becomes 0, which is expected since there is no carrier component in this case. Peak amplitude of the DSB SC modulated voltage is given by A is equal to Em. A is nothing but A equal to Em sin omega t. You can replace Em sin omega t in place of Em. So as we know, modulation index M is equal to Em by Ec. The main equation becomes Em is equal to M into Ec. Can replace this value in the given equation. So the instantaneous voltage of resulting amplitude modulated wave can be represented in sin A into sin B form. Sin A into sin B. So as we know, sin A into sin B is nothing but 1/2 cos of A minus B minus cos of A plus B. That is the standard equation. So replace the value of cos of A minus B and cos of A plus B in the above equation. So new equation becomes E of DSB SC is equal to, with two terms USB and LSB. This equation consists of LSB term as well as USB term, and n by 2 EC cos of omega C minus omega MT having LSB as well as USB n by 2 EC cos of omega C plus omega MT. Next is the time domain representation of DSB SC wave. The amplitude top envelope of DSB SC is given by, according to this wave diagram, Em sin omega mt, and also consists of bottom envelope with negative value, that is minus A is equal to minus Em sin omega t. Bottom envelope is shown with dotted line as in this wave diagram. The top envelope crosses below 0 reference amplitude value, and similarly bottom envelope crosses above 0 reference amplitude value. In case of AM wave, top envelope can touch to 0 reference but cannot cross it. The information can be recovered from top or bottom envelope. So for suppressing the carrier, we have to pay price in case of DSB SC. Next point is power in DSB SC, that is double sideband suppressed carrier. Here carrier component is suppressed in DSB SC wave. The modulated wave contains energy only due to two sidebands. The amplitude of the sidebands depends on modulation index of Em by Ec. Total power in the DSB SC modulated wave will also depend on modulation index. So DSB SC is equal to E square LSB upon R plus E square USB upon R. As we know the formula, AC is equal to E square upon R, where all the voltages are RMS values of R, and R is the resistance in which power is dissipated. So replace E square sidebands upon R with these values and we simplify the equation as EC square upon 2R into M square divided by 2. So as we know, average carrier power EC upon root 2 bracket square upon R, and TC is equal to E square upon 2R. So power dissipated here in DSB SC is equal to TC into bracket M square divided by 2 is the total power in DSB SC modulated wave to the unmodulated carrier power. When M is equal to 0, so we can put here value of M becomes 0. Then power is nothing but TC divided by 2, that is 50%. Thus we need only maximum of 50% unmodulated carrier power for the transmission of this DSB SC wave. So in this way, this lecture we have discussed DSB SC point. Okay, thank you.